Hi everybody, it's a pleasure to be here in the meeting, and I'd like to thank the organizers for inviting me to give a talk. I was speaking about the dimension that is typically hidden in fault simulations. This hidden dimension is the one that transects the fault at the outcrop or sample scale. Though it may be small, I will try to demonstrate that it may harbor some interesting complexity that could be of relevance to us modelers, because resolving it, even at an artificially inflated scale, will allow us to step away from the explicitly meshed, predefined fault plane and instead make models that are less reliant on a priori information and thus potentially are more predictive. I will first briefly outline some basic theory and a problem that we have identified. I will then motivate our theoretical solution to this problem, and I will show some results of this solution in simple numerical models too. While our model fixes some existing computational issues, it also introduces new resolution requirements. I'll be commenting a bit on the issues we're facing and the solutions that we're thinking of before I finish the talk. Most of the materials presented here were published earlier this year in JGR Solid Earth. The reference is given at the bottom of the slide. There you will also see a list of people that have been involved in this work, at least which has since grown. These include Patrick Senon from HH, Laetitia Lepourier from Sorbonne Université in Paris, and Dave and Alice from Scripps, both present here in this meeting. I've been having a really spotty internet connection as of late, hence the pre-recorded talk, but I nevertheless hope to be able to answer any questions you might have in a panel discussion. If not, please feel free to email me at the Gmail address listed above or my institutional email address you'll find online. I'll start off with a few simple observations that should not be news to anybody listening. Rocks in the Earth's subsurface are generally polycrystalline, granular materials, and faults are lamellar regions of intense deformation within the rock mass. In the field, faults can be distinguished by existence of broad zones of damage in the form of more or less intensely cracked and incoherent rocks, but also by a host of more subtle characteristics like microstructure, mineral phase assembly, chemistry, etc. Importantly, at least for the sake of this presentation, faults are characterized by a strong orders of magnitude reduction of grain size and the formation of so-called fault gouge. You see this effect reproduced in a lab setting in the figure on the top right from Pozzi and co-workers, and sketched on the bottom right in one of Sylvain's recent works. I'll make an example of grain size, but that is not to say that any of the other fault features are not important. Much of what I will be motivating from the perspective of grain size could be applicable to other mechanisms too. It's known that fine-grained media deform more readily than coarse-grained media. Under deformation, elastic energy dissipation causes the diminution of grains or a reduction in grain size. This forms a runaway mechanism that can trigger earthquakes, as reduced grain size over time causes more intense deformation, which further reduces the grain size. In the absence of kinematic processes, on the other hand, grains steadily grow in order to minimize their surface energy, which provides a healing mechanism. Other faulting mechanisms may exhibit trajectories that are similar, and a string of authors have made useful physical models of fault friction over the years. I'll continue with the recent work of Sylvain that was published in Tectonophysics, in which he provided an elegant physical explanation of rate and state friction as the thermally activated creep-and-grain junctions. His model presumes the existence of a shear band with a definite and known width L and a known orientation with respect to the principal stress axes. In the list of ingredients shown between the diagrams on the right, you'll furthermore find the friction coefficient F as the ratio of shear stress over the normal stress, which again requires a known shear band orientation, as well as the slip rate d dot across the shear band. From the width and the slip rate, a uniform distribution of anelastic shear strain gamma dot can be derived. Lastly, the model assumes a representative grain size and postulates that what we all know as the state variable in rate and state friction models is simply proportional to the grain size raised to some power p. A fairly well-established grain size evolution model shown in the first equation on this slide then transforms to the aging law that we all know. Note that I've taken the liberty of adding the friction coefficient as a normalized measure of the shear stress into both equations in order to form a thermodynamically sound dissipation term. Since the friction coefficient is on the order of 1 and changes relatively little, this should leave the aging law more or less unaffected. Here I take inspiration from the work of Rosell and co-workers published in 2011 in Geophysical Journal International. As explained in Sylvain's work, because smaller grains experience stronger stress concentrations at their junctions, they slide more readily past each other. This is diagrammatically explained in the figure on the bottom right of the slide, also taken from his paper. This gives rise to a relatively straightforward power law rheology as shown in the second equation, where the friction coefficient depends on the effective anelastic shear strain rate raised to some power a times the state variable raised to some power b. A Taylor series expansion then leads to the well-known logarithmic form of rate and state friction. I should note that I have assumed that the grain size dependent rheology has been thermally activated and dropped the Arrhenius term from this equation. Now we get to my more nefarious motivations for taking this physical model of fault behavior as an example. Taking it at face value, we can identify two significant problems. The first one is that in a continuum, the shear plane is not uniquely defined, which complicates the definition of a friction coefficient. Luckily, this problem can be relatively straightforwardly resolved by extending the notion of internal friction using existing theory. More serious is the assumption of a uniform and non-strain distribution. Such an assumption is not always in line with the natural observations, especially of younger and geometrically complex fault zones, and thus may neglect interesting and potentially observable phenomena associated with faulting and rupture. I'll come back to these potential phenomena in a few slides. Moreover, we know that the strain softening rheologies are associated with strain localization. In the case of rate-and-state friction, this effect can be so severe that the distribution of strain approaches the direct distribution in finite time, which inevitably leads to spurious resolution sensitivity in numerical models. The end result is that either the model is collapsed onto a plane using the assumption of uniform strain and simulated the traditional way, in which case potentially interesting phenomena are ignored, or the model is implemented in a continuum, but information is lost due to unavoidable mesh sensitivity issues and convergence cannot be guaranteed. The question that we've tried to address is this: can we overcome these particular issues in some practical and theoretically sound way without sacrificing agreement with existing observations from the laboratories? The end goal of this question is again to reintroduce a potentially interesting dimension to fault models that is typically neglected for practical reasons. As an aside, one could argue that I've taken a pathological case because grain size evolution has no intrinsic diffusion, unlike, for example, temperature, pore fluid, or chemistry-dependent processes. Such a diffusion process would regularize the mesh dependence. However, diffusion length scales around faults in nature are typically very small, far beyond the reach of resolution in large-scale models, and cannot be artificially increased to fit the practical model constraints without fundamentally altering the rheological behavior. The same goes, by the way, for viscous damping, which is sometimes advocated as a solution to the localization problem. Anyway, onto the theoretical solution we've developed. The time and slip dependence of friction was firmly established by James Dietrich and others in the late 70s. In his PhD thesis defended in 1980 and his famous paper published in 1983, Andy Ruina formalized the observed behavior as the temporal convolution of the sliding history with a kernel function that represents the fading memory of the fault. He showed that for a particular choice of kernel, the exponent of the negative dimensionless time, the result can be differentiated to form the aging law that I showed on the last slide. Here we simply extend this idea to the spatial dimension. We posit that grains never move in isolation, but form force chains that are continuously being broken and reconfigured. It is therefore not unthinkable that deformation in granular media knows some kind of fading influence with distance away from a point, and we take the same exponent of negative radius as a convolution kernel. This kernel is plotted, by the way, in the top right figure. After convolving the anelastic strain gamma in this way to give a non-local equivalent gamma bar used in the dissipation term of the aging law, we show that the Taylor series expansion of gamma bar gives rise to the additional Laplacian term. Note also the automatic introduction of a length scale lambda with this term, which can be physically interpreted as some multiple of the grain size. I should note that the idea of convolving the anelastic strain rate in the dissipation term was first introduced by Norm Sleep in his fantastic 1997 paper on a unified rate-and-state friction theory. But it was never very well motivated from a theoretical point of view, something that we have been able to do. Although it's not immediately obvious, we showed that after some manipulation, the rheology can be modeled as a reaction diffusion equation for which analytical solutions of limit cases can be derived using established techniques. One such family of solutions of the limit of most extreme localization is plotted in the middle figure for a range of values of A and B, expressed here as the ratio of the two. We see a wider localized strain rate distribution for more stable frictional regimes and narrower localized distributions for less stable regimes, but we can always obtain a finite distribution of anelastic strain rate as a function of the length scale lambda. We can thus show that the problem of spurious localization has been resolved by introducing the Laplacian term. Importantly, we can artificially inflate the value of the length scale lambda to be tied to the mesh resolution rather than grain size, provided that the resolution is sufficient to allow for some kind of separation of scales. The next question is then, can this regularization term be freely introduced without affecting the rheological behavior, especially as lambda is artificially inflated? The answer is yes, up to a point. I will show this using numerical results on the next slide, and I will come back to this important issue later on, but a convincing theoretical argument I will have to refer to our recent paper. Finally, I mentioned the ambivalence of friction in continuum models. We replace the interfacial friction coefficient with an internal friction coefficient, which is calibrated to the Mokulov or Drucker-Parger models in the yielding limit, and is regularized to become essentially frictionless at sufficiently large tensile stress. The value of the friction coefficient is plotted in the Moore plane in the figure on the bottom right, where increasingly darker colors show increasingly high values of friction, and where sufficiently high values of the friction coefficient presents such a large driving force in the anelastic rheology that certain stress states are effectively forbidden. This is conceptually visualized by the white region where friction becomes much larger than 1, but in reality this effective barrier will occur at lower values. It should be noted that any stress state has a definitive friction coefficient, even very far away from effective yield, and that the friction model in its most recent iteration contains no singularities. Now I'll describe some numerical results developed on a simple one-dimensional transect of a gauge layer subject to simple shear conditions. All complexities related to internal friction that I've just mentioned can be forgotten because in this configuration only one shear plane is possible and the stress tensor has only two components, shear stress and normal stress. In the first model, we replicate the famous velocity stepping laboratory setup that formed the experimental basis for the development of rate-and-state friction. The stepwise driving force and frictional response are shown in the figure on the left, which was taken from Andy Riena's 1983 paper. As a reference, we take a point model of the established interfacial rate-and-state friction and aging law, and compare this to a one-dimensional transect of the experimental gauge layer that models the continuum friction process with the proposed regularization. Both are subject to the same oscillating boundary condition with sudden factor 100 increases and decreases of driving velocity v, with a period of 50 times the critical slip weakening distance d sub c. We do consider the effective slip weakening distance of the continuum model to be a tunable parameter within reasonable bounds, as this parameter in reality arises as an emergent property of the model from the critical strain and some moment of the strain rate distribution. The response to sudden velocity increases and sudden velocity decreases of both models are recorded in the figure on the bottom right, in which the classical interfacial model is represented by the thick yellow line and the regularized continuum model by the thin dark blue line. We see that both models respond nearly identically to sudden increases or decreases of the slip velocity after only minor tuning of the effective slip weakening distance, which again we consider a reasonable thing to do. More interesting is the response plotted in the top right figure, where the left panel shows the oscillating driving force and the right panel shows the corresponding distribution of anelastic strain rate across the gauge layer. Lighter colors correspond to larger strain rates, but each profile is normalized to better show strain rate locality. We clearly see that a positive velocity jump is associated with direct localization and evolving delocalization towards the steady state, and that conversely a negative velocity jump is associated with direct delocalization and subsequent evolving localization. In other words, locality of deformation follows the frictional response. This is an interesting prediction of the model that could in principle be recorded in laboratory experiments, though I'm not aware of any such data. I imagine that it would require post-mortem analysis, and it might be challenging to find a minimally intrusive way to stop an experiment to properly record the response. In the next model, we keep everything the same, but massively increase the domain size to the crustal scale and apply constant tectonic loading at one end of the domain. This model produces a regular sequence of frictional instabilities that can be interpreted as earthquakes and shows much more interesting cross-fault behavior. In the figure, I've plotted the cross-fault strain rate profiles in the same color scheme as before, where bright yellow colors denote large strain rate. In this case, however, the color scale is logarithmic in order to emphasize the massive lateral transients. The cross-fault distance is measured in length scales lambda and plotted on the vertical axis. The horizontal axis is more complicated. Let me try to explain. In order to focus on the interesting phenomena that are happening around each event, I have plotted the cumulative time step number on the horizontal axis. I have, however, made the odd choice of labeling each single event with a number between 1 to 7 on the horizontal axis. The last event is magnified with respect to the others in order to better show the localization phase. Recently, Nadia pointed out to me that a lot of confusion can be avoided if I would simply plot the full transect versus cumulative slip, which works because the adaptive time step is roughly inversely proportional to the maximum strain rate. So for the sake of argument, you may read the horizontal axis as approximately the cumulative slip measured in units of total slip per event. Because of this scale, the intersection period is essentially not visible as it is collapsed to the thin dark blue lines between events. Again, I emphasize that the vertical axis represents the distance across the gauge layer measured in lambdas, which may be arbitrarily large or small. We can see that each event follows the same pattern of broad activation of background deformation, followed by a nucleation phase in which strain strongly localizes. Localization is arrested as the Laplacian term gains influence, but activation of anelastic processes continues to escalate. At some point, the event starts to develop quasi-dynamically. Because we assume static momentum balance, we've had to introduce some continuum equivalent of the radiation damping approximation. In our model, this also takes the form of a viscous damping term, which interacts with the continuum rheology to cause strong co-seismic delocalization, another feature not captured in the interfacial fault models. We do expect the same effect when replacing the radiation damping approximation with true seismic radiation, but we'll be sure to try this in future models. After some time, the event arrests and continues to delocalize in the post-seismic phase, and the cycle repeats. Interestingly, the response recorded by integrating the anelastic strain rate over the profile to form an effective slip rate differs co-seismically from the equivalent interfacial model response. We are not very worried by that discrepancy, since the model setup is on the one hand beyond the reach of laboratory results in scale, and on the other hand geometrically still too simple to be compared to natural data. Further model developments in 2D and even 3D, as well as the inclusion of inertia, should lead to more discriminatory predictions. For the last numerical modeling result, we move to 2 dimensions, but reduce again the complexity of the frictional response. A friendly region of parameter space is found by choosing A and B equal to each other and both rather small, choosing D sub C similarly small, and choosing a steady state friction of 0.6. A square domain that reflects a thick gauge layer is loaded from all sides in a right lateral simple shear mode, and a smooth initial perturbation of the anelastic strain rate is set in the center of the domain. The frictional response is stiff and plotted in a yellow line in the figure below versus slip or equivalently strain. The blue line in the same figure gives a spontaneous evolution of the effective anelastic strain rate, which starts out really small. Initially, the frictional response closely follows the elastic response as anelastic strain remains negligible. Then, at a critical amount of elastic loading, the effective anelastic strain rate very suddenly increases to some value larger than the steady state value. This leads to a strain softening response. After some further strain, the model converges on a steady state of stress and strain rate. The choice of parameters thus causes the rate and state dependent friction model to converge on an effectively linear strain softening plastic model. We use this to model plastic shear bands, with the distinction that the non-local influence of softening not only regularizes shear band width to a predetermined multiple of the mesh resolution, but also facilitates lateral migration of shear bands not typically encountered in plasticity models. I'm going to play a movie of the model evolution, and we'll be showing the effective anelastic strain rate in bright colors in the top left panel, the accumulated anelastic strain in similar color scale in the top right panel, the vorticity in the bottom left panel with left lateral motion in blue and right lateral motion in yellow, and finally the friction coefficient in the bottom right panel with again largest value in bright yellow and lower values in dark blue. If you're unsure what to focus on, I can suggest looking at the vorticity in the bottom left panel. We can see that the radially symmetric initial condition decomposes into 2 conjugate sets of shear bands in a diamond shape. Since friction is larger on the exterior of the shear bands than on the interior, outward migration occurs, which is facilitated by the gradient dependence of the softening term. 2 sets of conjugate shear bands is 1 set too many, and as the initial symmetry becomes unstable, 1 set starts to become dominant. The simulation is stopped when the shear bands get sufficiently close to the domain walls. I'm going to play the movie again without commenting because I think it's rather beautiful. And one more time. Finally, I overlay the top left panel with the theoretical Arthur and Coulomb angles, which are predictions of how shear bands should orient themselves with respect to the principal stress axis. We see that excellent agreement with the Arthur angle is observed, and this is thanks in large part to our ability to attune the shear band width to some multiple of the mesh resolution in advance using the length scale lambda. What we may learn from this simple model is that in a sufficiently thick uniform gauge layer, a lot of interesting internal complexity can develop. We're working on 2 dynamic rapture models that may demonstrate this more convincingly. I wanted to expand a bit more on the computational challenges that we're facing when upscaling these simple models and the techniques that we're working on to defeat those issues. As I've said, the value of lambda has minor influence on the aggregate results up to a point. In fact, in simple one-dimensional models, the value of lambda does not have any influence at all, as it simply represents a scale factor of the coordinate axis. In higher dimensions, however, the situation is more complicated. Because the Laplacian term formally acts as a diffusion process, care must be taken not to diffuse away some of the important long strike length scales of nucleation and rupture propagation. This can be ensured by choosing, for example, lambda to be significantly smaller than the cohesive zone size big lambda. A good choice would be to set lambda equal to, for example, 1/5 of big lambda. Small lambda, however, must still be resolvable, and this results in a 5-fold increase then in the resolution requirements in each dimension. Currently, seismic cycle models are already strongly constrained by the resolution requirements. Increasing the computational efficiency by a factor of 5 squared or even 5 cubed is not going to be an easy task. I'll come back to this on the next slide. All in all, I've tried to motivate my view that near-fault complexity can probably be resolved at an artificially inflated scale, provided that this is done in a very specific way. The only ultimate requirement is that the resolution of the model is sufficient to facilitate a separation of scales between elastodynamic or background processes and the anelastic processes that govern fault behavior. I think that when choosing a numerical methodology to tackle this challenging issue, boundary integral methods are a no-go. Although I have seen some interesting ways in which a boundary integral element method may be used to supplement other methods in this meeting. As a domain scientist rather than a computational scientist, I think that sufficiently performant higher order finite element methods with adaptive mesh refinement are far beyond my capabilities and beyond my area of interest too, to be honest, even though they would be an excellent choice. Particle-based methods could be a suitable choice too, but the same caveat applies, although maybe to a lesser extent. Therefore, partially due to my own inertia, we've settled on the finite difference method, which is conceptually not so hard, relatively straightforward to implement, and even reasonably straightforward to parallelize. For the moment, we have ditched our existing finite difference codes and have started to collaborate with Ludovic Reis from the glaciology department at ETH, who has been involved over the years in a collaborative effort to develop a series of modeling paradigms and corresponding Julia packages for finite differences that have really pushed the boundaries of grid resolution. The figure on the right shows a simulation of time-dependent reactive fluid chimney formation in porous sediments that was run at a resolution of roughly 6,000 cubed grid nodes and was run in parallel on all 5,000 plus GPUs of what was then the Pitstein supercomputer in Lugano, Switzerland. The model combined simple second-order accurate staggered grid finite differences with rather primitive semi-iterative solution methods, which leads to optimal locality of computation, high computational throughput on the GPUs, and excellent parallel efficiency. We have been working to improve convergence of those semi-iterative methods and to develop an efficient time integration scheme for the more stiff frictional problem, which treats non-stiff terms explicitly and decouples stiff scalar or PDE components into a sequence of implicit problems for optimal time step control independent of grid resolution. Of course, any useful result will be released into the public domain. On the topic of current research directions, we have asked ourselves the question, what process creates the gouge layer in the first place, and can we model it? A possible answer is to interpret the proposed internal rate and state friction law as the breakage component of the damage-breakage model of Liakovsky and Benzayan, iterations of which have been published over the years in various journals. The damage parameter alpha reflects the fractured state of the subsurface, where increasing values of alpha reflect increasingly densely fractured media with reduced elastic moduli. The presence of gradients of alpha, or in other words, regions of crack tip concentrations, causes so-called structural stresses. This is subject to diffusion as the structural stresses tend to equilibrate. Beyond the critical damage level, the rock loses all elastic coherence and starts to flow as a granular material. This granular flow can be implemented as internal rate and state friction with only minor changes to the damage breakage model. Most notable of which is the inclusion of a diffusion term in the evolution law of the breakage field beta. We thus end up with two coupled diffusion equations where the nonlinear diffusivities can themselves give rise to interesting scale interactions and separations. Of course, this would give rise to even more serious computational challenges as well. We are working to add damage evolution to our existing models in order to better capture the complete process of fault evolution. In conclusion, we have taken a physically motivated form of the rate and state friction and argued for its extension to the fault perpendicular dimension by introducing an interactional length scale. We have also argued that to some extent, when done carefully, the length scale can be artificially scaled up to meet modeling requirements. There are of course limits to this, and numerical models have to be of sufficiently high resolution to facilitate the separation of scales. Most likely, techniques developed here can be used to upscale other fault processes too. For example, the thermal evolution would be an interesting next step. The ultimate goal of what we're trying to do is to increase the capacity of simulations to translate conceptual models into testable predictions. The predictions may be wrong, however, and that's okay for the moment. Our priority now is to focus on further developing the numerical techniques that we require. With that, I end my talk, and thank you all very much for sticking around.